me remind you the axioms of this seminar. Absolutely no electronic devices, laptops, smartphones, iPhones. Today's speaker is a co-organizer of this seminar, soon to be Dr. Nate Fox, who will talk about exciting new developments in Hofstadter-like sequences.
Thank you. So, yes, we talked about Hofstadter-like sequences. So what does that mean? So some of you have been to either my previous talk at this seminar or Douglas Hofstadter's talk at this seminar, in which case you would have seen Hofstadter sequences before. But not all of you were there, so I'm going to review what that is. So when I mean Hofstadter-like sequence, I basically just mean sequence defined by a nested recurrence. The basic example being the Hofstadter Q-sequence. So it's sort of like the Fibonacci sequence, but you'll see how it's different. So Q of 1 is 1, Q of 2 is 1. So it's the same initial condition as the Fibonacci numbers, but then for n greater than or equal to 3, Q of n is defined by the following nested recurrence. So for Fibonacci, it would just be Q of n is Q of n minus 1 plus Q of n minus 2. Whereas with Hofstadter, Q of n is Q of n minus Q of n minus 1 plus Q of n minus Q of n minus 2. So the previous terms tell you how far back you're jumping in the sequence. Yeah?
My eyes are a little bad. Can you write slightly larger?
I can write slightly larger, yes, but I have to not get through 3 or more boards before a certain part of the talk. So this sequence is in OAIS, sequence 5185, and the first few terminals 1, 1, 2, 3, 3, 4, 5, 5. I'm going to keep going until it gets interesting. So far it doesn't look so interesting. It's just some 1s and 2s. It's just increasing slowly. And then, oh, there's all of a sudden an 8 here. And then there's 2 more 8s. And then 10, and then I'm just going to stop at this 9 just to show you that it's not an increasing sequence. And then it keeps going. And the big question about this sequence is, does it even exist? Why might Q of n not exist? Let's see what could happen. So if Q of n minus 1 is greater than or equal to n for some n, then when we try to compute Q of n, let's see what happens. Q of n is, well, remember our recurrence, it's Q of n minus Q of n minus 1 plus Q of n minus Q of n minus 2, which is Q of something that's not a positive number. Plus something we don't really care about. This is the important thing. We only define Q of n for positive n. So theoretically, we might eventually have to evaluate Q at a non-positive index. So this is undefined. And as we remember from basically anywhere in math, undefined plus question mark is undefined. So Q of n and then every subsequent term undefined. So if this happens, we say that this Q sequence dies after n minus 1 terms. So in this talk, I'm going to replace the word dies here with weakly dies, because I'm going to define 2 notions of sequences dying. But I'm going to say when this happens, the sequence weakly dies.
Because you could have
change the definition.
Basically, there's going to be a prescribed way in which we're going to change definitions, and that will lead us to the notion of when a sequence strongly dies. Before we talk about sequences that can strongly die, that weakly die but don't strongly die, it's going to be the case that every sequence that strongly dies also weakly dies. But first, we're going to talk about another solution to the same recurrence that doesn't even weakly die, so it doesn't die at all. So the main trick up our sleeves is we're allowed to make the initial condition be whatever we want. So Hofstadter went with 1, 1. Golem gave the different initial condition, same recurrence, but q of 1 equals 3, q of 2 equals 2, q of 3 equals 1, and then for very greater or equal to 4, use that recurrence. And then the resulting sequence, I forgot to write down the A number for this one, but I've mentioned it. I mentioned it the last time I talked in this seminar. The sequence is 3, 2, 1, 3, 5, 4, 3, 8, 7, 3, 11, 10, and so on. And you don't even have to worry about things being, none of these terms is bigger than the next index. And so this is quasi-linear, meaning it's an interleaving of 3 sequences, and each one is either constant or linear. And it doesn't die. And it's easy enough to prove this by induction that this thing doesn't die. I'll just give you a flavor, or to prove the formula for it. If the formula is q of 3m is equal to 3m minus 2, so like q of 3 is 1, q of 6 is 4. Q of 3m plus 1 is always going to be 3. Q of 3m plus 2 is going to be 3m plus 2. So if you just try to compute symbolically in terms of m, well, what's q of 3m plus 2? Q of 3m plus 2 is q of 3m plus 2 minus q of 3m plus 1 plus q of 3m plus 2 minus q of 3m. And q of 3m plus 1 is 3, so this is q of 3m minus 1. And q of 3m is 3m minus 2, so this is q of 4. So q of 4 we know is 3. So this is just the previous iteration of this guy, because this is 3 less than that, plus 3. And sure enough, you plug in m minus 1 here, it drops by 3. So this proves it for this guy, and then you can do the same thing for the other two, and you get an easy proof. And importantly, this proof, a computer can do this proof very easily also.
Can a computer conjecture that very easily?
Yes, a computer can also conjecture that very easily. That was what my last talk was about. The last talk I gave in this seminar was about computers conjecturing things like that.
So
this talk, we're assuming that we can do that, okay, and we're going to do other things.
So you give them that sequence, the computer can conjecture and prove. And
even what I talked about last time was I give the computer the number 3, and it finds that sequence because it has 3 interleaved sequences. But yes, if you give the computer that sequence, it can easily guess that that's going to be the form, and then it can write that symbolic thing down and prove it. So I said that thing about weak death versus strong death. So we're going to cheat and say we're allowed to define q of n to be 0 when n is not positive. And again, this is not necessarily the same initial condition as Hofstadter, and it's usually going to be the same recurrence, but sometimes it will even change the recurrence. But even if we do this, sequences can still die. And the reason that can happen is you can have non-positive terms appear in the sequence. In particular, you can get a 0 at some point. Because like I say with the Hofstadter recurrence, you're computing terms, and then you get 2 really big terms in a row. So the first really big term, you can handle that. You just get 0 plus this question mark. But if you get 2 really big terms in a row, you get 0 plus 0, and then the next term is 0. And then what's q of the term after is 0? Well, it's self-referential. So we say it dies at that. So sequences can still die if q of n minus 1 is less than or equal to 0. And it'll pretty much always be equal to 0. There's some stupid ways it can become negative, but if we're not being stupid, it'll just equal 0 at some point. And if this happens, there's no way around this besides just arbitrarily fixing q of n, which even sometimes you can't do because you might get unlucky and say q of n is equal to q of n plus 5. And we say that things strongly die in this case, because there's no way to fix that. All right, so this has sort of set the stage for everything we're about to keep doing. So I'm going to pause to see if there's any questions right now before we start doing stuff with these notions. Okay. So what we're going to talk about today is defining many different families of solutions, mostly to that recurrence. So I'm going to show you pictures over the course of this talk of about 30 sequences. Most of them satisfy that recurrence. So I'd say I think about 25 of the 30 pictures satisfy that recurrence. But they almost all look very different from each other. So we've already seen, well, I haven't shown you the picture of this guy yet, but I will. And I'm not going to show you a picture of this guy, but it looks like 3 lines. But an interesting thought I had at one point, and I decided to play around with, was what if we give the Hofstadter recurrence, the initial condition, 1 through n, for some n. So q of I equals I for 1 less than or equal to I less than or equal to n, where n is a parameter. So it should be clear what happens if n is 2 or 3. Well, if n is 1, you can't compute q of 2, so n of 1 is stupid. If n is 2, we're actually going to just get Hofstadter sequence, but it's going to be offset by 1. Because one nice thing about this type of recurrence is if you shift all the terms of the sequence, it still satisfies the recurrence. So the fact that the Hofstadter sequence starts 1, 1, 2, we might as well just shift it over and start it with 1, 2, and we get the same sequence. And for free, we also get that 1, 2, 3 gives us the same sequence, because after we compute the third term, it's a 3, so that's going to clearly be the same sequence. But the fourth term in that sequence is a 3, not a 4. So starting with 1, 2, 3, 4 might give us a different sequence. And sure enough, it does give us a different sequence. So I'm going to show you a few of these. So this is for 1, 2, or 1, 2, 3. So this is what the Hofstadter sequence looks like. This is the first, I guess, like 50,000 terms. And it has this sausage-like structure that no one's been able to actually prove exists. But then if we start changing the initial condition 1, 2, 3, 4, you can still see, I think, of that sausage structure. But it's not nearly as precise. You can still see it's kind of like wavy. And this is soon to be the A number of this sequence. I've put it in there. I haven't submitted it yet, but it's reserved for this sequence. Like any A number in this sequence in this talk that starts 278 or 274 has not been officially submitted yet, but it has been reserved, and that will be the A number for the sequence.
Are the sausage places the same?
They look about the same, don't they?
Okay.
I haven't like checked to see if they're the same. I haven't really analyzed this sequence much. Like the Hofstadter sequence, I have no clue that I can't, like this thing, I've computed 30 million terms of it. It exists for 30 million terms. And similarly, the sequence for 5 exists for 30 million terms. 6 exists for 30 million terms. And notice the sausage structure is still kind of there, but it's gone away. You can still sort of see it with 5. 6, you have to squint a lot to see it. And from 7 on, you won't be able to see it anymore. So this one I actually computed 100 million terms and it doesn't die in the first 100 million terms. But this one's 9. So I skipped from 7 to 9. Why do you think I did that? 8 dies. So n equals 8 dies after, I don't remember exactly how many terms, it's 400 something terms. Because you get a term like Q of 409 is like 419 or something, and then it dies. But the 9-1 doesn't seem to die. The 10-1 doesn't seem to die. 11 and 12 die. 13 doesn't appear to die.
Can die after a very long time.
I mean, the 8-1 dies after 400-ish terms, but all the ones that I don't, that's the longest one that I know of that does die. I mean, that's not completely true, because the theorem I'm about to say is going to be that everything 14 and bigger dies, but the length of time in which it dies, so clearly if I feed it like n equals 5 billion, it will die after more than 5 billion terms, because the initial condition has length 5 billion. But so 13 doesn't appear to die, but we have a theorem. For n greater than or equal to 14, I'm going to call this, just shorthand, this sequence is Qn of n. So the subscript n means initial condition 1 through n. The theorem is for n greater than or equal to 14, Q sub n of n dies, and for n greater than or equal to 21, it dies after n plus 28 terms. For 14 through 20, it dies after like 4 or 5 more terms. I think it's n plus 33. I have that here. Yeah, n plus 32 is the last term in the case that it's 14 through 20. But the thing is, these all have the same behavior.
Will they strongly die or weakly die?
Right now, right now I'm talking about weekly die.
Okay.
So these, for most of the talk, I'm going to be talking about things strongly dying. But here I'm talking about them weakly dying. So as soon as we get a term that's bigger than the index, it dies.
Was the n is equal to 8 one? Was that strong death?
No, everything is weak death. Okay. These 8, 11, and 12, I actually, when I was trying to get the terms to put it in the OAS, I was getting more terms than I remember. I was like, why isn't this thing dying? It's like, oh, because I forgot to set it to check for weekly dying. So these all have the same behavior. So in my title and abstract, I talked about nonstandard integers. So basically what a nonstandard integer is, it's just some symbol n that's bigger than any natural number n, but it can still have various number theoretic properties. In particular, it has certain congruences, mod, anything. So like, for example, you can have this symbol n, but you could say, oh, n is congruent to 0 mod 5. So for this particular theorem, we don't need any congruence properties of n, but the way we tend to prove theorems like this we just calculate terms using a symbolic n. And sometimes we find we need congruence properties. In this case, we don't, but in basically all the other things we will. So I'm going to compute one term of it, and then I'll just show you the rest of the terms. Can people see if I write here? Or should I go back over there? I think I'll just write it here. So we have the initial condition of 1 through n. So what's Q of n plus 1? Well, it's Q of n plus 1 minus Q of n plus Q of n plus 1 minus Q of n minus 1. But we know that Q of n is n. So this is Q of 1. And we know that this is n minus 1. So this is Q of 2. And then we know Q of 1 and Q of 2. So we get 3. But we assumed something. We assumed that n was bigger than 2. Because otherwise, this Q of 2, or n is not 1, so it could be 2. But as long as n is greater than or equal to 2, this worked. Because otherwise, Q of 2 would not actually equal 2. So whenever we write Q of just some number, and we use that value when doing this calculation, we are assuming that that n is bigger than that number. So we can continue like this. So Q of n plus 1 is 3. And then we get Q of n plus 2 is n plus 1. And then we just keep going. And at various points, we use various other values. In particular, I believe to get this one, we use the fact that Q of 11 is 11. We don't even use the Q of 13 is 13 somewhere. But then when we get to n plus 28, we get that Q of n plus 28 is 2n plus 8. So if n is this like huge number that's bigger than any natural number, this is clearly just bigger than that. So Q of n plus 29 doesn't exist. But we can actually figure out exactly how big n has to be for that to be the case. And it turns out n greater than or equal to 21 would mean that 2n plus 8 is greater than or equal to n plus 29. N plus 29 is the next index. And that means as long as n is greater than or equal to 21, we have the initial condition plus these 28 terms. Just instantiate n with whatever value you want. So all these sequences weakly die, as long as n is big enough. So the only ones, so the ones that I've shown you pictures of, those are the only ones in this family that don't potentially weakly die.
Or that potentially don't weakly die.
I think I said that. I may have missaid that, but I mean, I just invented the term weakly die earlier today to try to make it clear what I meant by sequences dying. So I misused it. I apologize.
So it's possible if n equals 9 it does die, you just didn't go far enough.
N equals 9? Was that one of the ones I showed here? Yeah, it's possible. It does not. It's not possible that it dies in the first 30 million times. But it's just as possible as the Hofstadter sequence is dying. In fact, it's probably a little bit more possible because it looks a little bit more chaotic.
Yeah.
The Hofstadter sequence, you can see a pattern. 13 and 9, you can't really.
It looks like you should take 13 and run it out a really long way.
I did. I mean, I took 7 and ran it to 100 million. I may have done that for 13 as well, but I don't have a record of doing that, so I can only confidently say that it lives for 30 million terms. But I may have calculated it for like 100 million. But I could do even more if I felt like it, and I should do that at some point.
Well, you took Reckoman out to 10 to the 230.
I don't expect to do that. All right, so these guys all weakly die. So for the rest of the talk, we'll talk about when do things strongly die. And for perhaps the rest of the talk, depending on how long it takes, we'll talk about when do these sequences strongly die. So now, rather than just say, oh, we're dead when we get here, we just say that Q of n plus 29, this term zeroes out and it's just Q of n plus 9. So Q of n plus 29 in this context would just be n plus 6. And then we can keep computing more terms. So the general method for what to do in this and other situations is, so this is the general algorithm, which is a real pain to implement because you have to worry about so many intricate cases. So step one is you generate a bunch of terms symbolic. Generate a bunch of symbolic terms. Sort of like we did over there. So this one we generated terms and it died. But maybe sometimes it will die even over here. So you just generate a bunch of terms, and if you're lucky, it dies. Because then you can stop, and you don't have to try it anymore. But it often doesn't die. You often get something, and there's lots of patterns. So then, what I try to do in looking for these, this may not be the most general thing you can do, but this is what I am doing, and it's worked in a lot of cases, is you take your symbolic terms and try to write down a quasi-polynomial that they eventually satisfy. You want? So something like Golomb sequence. recurrence. And in fact, this algorithm would even work to prove that Golem sequence exists forever. But this is, I would say, a bit overkill for that. And then step 3 is try to prove that that quasi-polynomial formula is correct, just inductively. But proving the formula has 2 issues. We've seen one of those issues already. That issue being, when we're proving the formula, we have to refer to other values of the sequence. So we need to know where those indices are. In that case, the only possible thing is the index we're referring to non-positive in the initial condition or after the initial condition. Those were the only cases over there. But in general, you might have run this algorithm a few steps. So you might have the non-positive index, you might have the initial condition, but then you might have this other quasi-polynomial piece that itself has an initial condition that you got out of the first iteration, but then you try to keep going. So then you're trying to evaluate this, you're trying to prove this new quasi-polynomial, but it's referring to guys in the previous block and in the initial condition and the negative guys, and then you could just keep going. So you have to be really careful with this and carefully look at what you're evaluating, and in particular, whenever you evaluate something in a different block, that's a constraint on your symbolic, I'm going to call them non-standard integers. But you can think of them as non-standard integers, or you can think of them just symbols that have number theoretic properties.
But the computer has to be careful.
Yes, the computer has to be very careful, and it has to keep track of all these assumptions it's making. So if you keep track of assumptions produced by referring to terms. And there's another issue that could crop up, which is this quasi-polynomial might last for a very long time, and if n is larger than every natural number, it might last length in terms of n. So if you're generating finitely many terms, you'll never see it stop. But really, it only lasts until you get to a certain point, and then it stops working because you've crossed some boundary and this proof fails. So the other thing we have to do is figure out how long this lasts. And then once you've done this, you have some sort of constraints on your symbol, and then you can just keep going. And sometimes it'll say, oh, it never dies, like in the Golem case, but usually that won't happen. In which case you just keep running this until it dies, or occasionally till it just doesn't work, which does occasionally happen. So I ran this algorithm on these guys, and somewhat surprisingly, this thing the congruence of n mod 5 determines the behavior of this thing, but it doesn't completely determine it. And I have no idea what's actually going on. I was talking to some of you guys yesterday about how I was having trouble writing down a conjecture. This is the conjecture that I was really struggling to write down. But I'm going to do my best to explain it to you guys. So this is the strong death, the behavior under strong death of that. So there are 4 possible eventual behaviors. So one is you get to a certain point, and then you generate 4 more terms, and then you die. And that certain point, I will try to make that more clear at some point. So case 1 is you get to a certain point, die after 4 more terms.